This video will be explaining and analyzing Project 3 of 2EI4 in the winter term of 2024. Today's date is Tuesday, March 19th. My name is Matthew Jarzynowski, and my student number is 400-455-803. Yeah, so this is the circuit schematic for the linear power buffer in Project 3, which has a near one-to-one linearity when simulated. As you can see here, the transistor chosen was of type BJT, and the overall topology for this circuit is that of a common collector. So I chose to use a BJT because a BJT usually has a low input resistance that will not alter the overall circuit resistance. Also related to MOSFETs, BJTs have, relatively speaking, higher fidelity as well as an overall better gain in their linear operating region. They're also considered faster due to their low capacitance on the control pin. And they also have the highest GM value, relatively speaking. And related to Project 2, you could say that since in Project 2 we used a lot of MOSFETs, why not switch it up and use a BJT? As discussed in the previous segment, the topology used of this circuit is of type common collector. Now, why is that? Well, the first reason is since we used a transistor of type BJT, we're given the choice of common emitter, common base, or common collector. But we can also consider the design spec. So the design spec relates that we should have less than or equal to 10% attenuation. Well, in terms of gain, that is approximately 0.9. Referring to this summary chart provided by Dr. Hadara in the Project 3's design guide, we can see that the common collector topology has a gain that is less than or equal to 1, satisfying one of our design requirements. We can also argue that to achieve this small gain, we will need a moderate or high input resistance, another trait of that of common collector. We can also say that the common collector creates a high voltage swing, as well as that it has a low output resistance, which when calculating the specific resistance values as well as just generally measuring the circuit simplifies our calculations. It can also be said that in terms of gain, if you were to have a small input resistance, you would have a high gain. This makes sense as the current flowing into the base of the transistor, given a small input resistance, would result in an overall higher amplification. Now we're going to go through the calculation process for finding the value of R1, R2, and discussing the chosen values for C1 and C2. Now, calculating GM, we're given that the magnitude of the input voltage is 0.5. We're also given that VT is approximately equal to, at room temperature, 25 millivolts. Using this derived formula, as well as some math, we find that GM must be greater than or equal to 990 microsiemens. Finding the input resistance, given the gain, that must be greater than or equal to 0.9, as well as RL and RS being 100 ohms. Using this derived expression, as well as some math, we find that the input resistance must be greater than or equal to 1 kilo ohm. So in calculating for R1 and R2, it is given that these values are arbitrary, that they must follow the relationship that Rn is equal to R1 in parallel with R2 in parallel with Rn prime, where Rn prime is given by this expression, where R pi is just R S divided by Gm. We find that Rn prime is approximately equal to 10.1 kilo ohms. Summing all these up, we find that Rn, given these two 10Ks, is approximately equal to 3.34 kilo ohms, which satisfies our initial design requirement. The values of the capacitors can be chosen as arbitrary as there's no real way to calculate these values. Thus, I just selected the capacitors from our 2EI kit as well as the 2CI kit and see which ones work best within the LT-SPICE simulation. Starting from the bottom, we can see a wave gen, which is a sinusoidal waveform with an amplitude of 0.5 at a frequency of 1000 hertz or 1 kilohertz. That is going into our source resistance at 100 ohms, our V in net, where we measure our input voltage, going into 100 microfarad capacitor, then into our resistor bias junction, which R1 and R2 are both 10Ks, going into our transistor, which the model of this transistor is TN3904, the same one that we have in our kit. Going up from here, we have a positive 5 voltage source, and going down, we have our second capacitor, which is 100 nanofarads, and our V out net, where we measure our voltage out, our load resistance, valued at 100 ohms, and our negative voltage source, valued at negative 5 volts. So for the simulation, I chose to run a transient analysis with the stop time set at 0.01 seconds and the time to start saving data at 0. The maximum time step was not relevant, as LT-SPICE automatically calculates that based on your stop time. Now, when running this simulation and selecting V in as our input voltage, which is in green, and selecting V out as our output voltage, we can see that they overlap, which is desirable in this case. To calculate the relative gain of this circuit, we can look at the simulation output graph, where we have our input voltage V in green and our output voltage V out in blue. We can keep on zooming in until we find a peak where we can place a cursor on V in, place another cursor on V out, line them up, and where V out is 483 millivolts and V in is 488 millivolts, we find that the gain is approximately equal to 0.99 within the design spec. To find the input resistance, we can simply apply Ohm's law, where resistance is equal to voltage divided by current. We can run the simulation, plot our voltage at V in, and since we know that current in a series loop is the same everywhere, we can say the current at the first capacitor. Find our voltage to be approximately 0.5 volts divided by our current, which in this case is approximately equal to 119 microamps, 116. Thus, our input resistance is approximately equal to 4.3 kiloohms, which satisfies our design requirement and our prior calculations. So this is the physical representation of the derived circuit in LT-SPICE. So this yellow wire is the 82 wavegen, supplying that sinusoidal input, going into our source resistor valued at 100 ohms. Now this red wire is our channel 1 of our 82, measuring our input voltage. That's going into a capacitor. Then that capacitor is connected to the base of our transistor, where from the base we also have those two 10Ks in parallel, where at the end here, those two 10Ks are wired directly to 82 ground. Now the collector of the transistor is directly wired to positive 5 VCC of the 82. And looking from the emitter, we go into our load resistor, which that load resistor is connected to, in this case, the negative 5 volts, which is also from the 82. Then from this junction, through this capacitor, we measure the output voltage on channel 2, also on the 82. Yeah, so this is the output of the physical circuit, where we have C1 in yellow as our input voltage and C2 as our output voltage. As you can see, these waveforms are relatively the same, and taking some measurements, we can see that Their peak-to-peak values are the same, their maximums are relatively the same, and their frequencies are the same. We can also take an average of the relative gain, where we have a custom math channel that just divides V out over V in, where our average is 0.99, which is above our design specification of 0.9. To determine linearity, we can take different values of amplitude for our input waveform. So let's say, for example, we'll start off at 250 millivolts. We'll go back to our scope, and okay, let's change our triggers, and we can see our maximum for both channel 2, our output voltage, and channel 1, our input voltage. We can divide these numbers to find our midband gain, divided by 250, which is approximately equal to 0.98, well within the project specification. Now we can repeat this process to, say, for example, 450. Well, we go back to our scope, run it again, stop it, take a measurement of 436 divided by 446, and we also get a gain of 0.98, also within the project specification. We can also use the spectrum analyzer to determine linearity. So if we run the spectrum analyzer, we get a lot of noise, right? But we can stop it, and we can see that the signal strength for both the output voltage as well as the input voltage is relatively the same, which is a good sign for linearity. We can also relate the scope in that our waveforms are clear and defined, in that thus we can conclude that this amplifier is fully linear.